good morning. The lecture is being recorded. So we will look at some other related topics about linear time invariant systems. So let's take, for example, two types of systems, differentiators and integrators. So we know that differentiation and integration are basic calculus operations, right? And it turns out that we can implement both differentiation and integration as circuits and systems and have them operate on signals. So let's say we represent the differential operator. It's a system which takes one input and one output. Input is x of t, output is y of t. So similarly, for the integration, we have a box. I. So t. And we can denote the operation differentiation as d over dx. Integration as integral minus infinity. So what this does is that whatever the input signal x of t, it finds the differential coefficient as a function of time, right? So this implements the function y of t is equal to d over dt x of t. Here it implements the function y of t is equal to the integral, some dummy variable x of lambda. First box will find the slope, right? We know that the differentiation operation gives you the tan, which is the slope. And the integration operation gives you the total area under the curve, basic calculus, right? So I can diagrammatically show that. Let's say this is my differentiation. This is time. This is x of t. Okay, similarly, this is time. This is x of t. I'm going to use the dummy variable. Let's say so lambda. It's lambda, right? That's just a dummy variable for calculus. And we have a function. So let's say this is the function. Like so. So what does d dt of x of t mean? It means the slope, right? So at some point in time, let's say this is my time, let's say t, or let's say t dash. The dx by dt gives you the slope, right? So this at this instance, if you draw a tangent, right? This tangent has a slope theta, which is a function of t. So the tan of theta is defined as d over bracket as x dot. That's fine. So imagine a function of time. So I can draw this slope like this. So as time goes by, this slope gives you the angle at which the function is changing. So similarly, we can also find the second derivative, right? If y prime of t, or say y2 of t is equal to d over dt of y of t, that is equal to d2 x over dt square. This is the second derivative. Okay. So we know that from basic calculus, when there is a minimum or a maximum, at every place where there's a minimum or a maxima, the second derivative will be the sign of the second derivative tells you whether it's a minima or a maxima, and the first derivative will be zero, right? Because the slope is zero. So these are basic calculus things. The reverse is happening for integration. In integration, we are not looking at the slope, but we are looking at the area under the curve, right? This is basic calculus. So let's say we take a time t. So from, let's say this is going to 0. So this is, let's say, at negative infinity. So we have the total area that's occupied by this curve. So this area as a function of t is equal to the integral so it keeps track of all the real estate under the curve from the time the curve started to now, right? So that's by definition. So it turns out that these two operations, differentiation and integration, are also falling under linear and time invariant operations. Okay. So let you take a picture. So I'll leave this part and erase this part. So let's take yt is equal to d over dt x of t. If I scale x of t, right, I get, let's say, k times x of t. So when I do d over dt k times x of t, this is a constant. So we know that when you have a function that's being differentiated and you add the constant has no effect, it just pops out of the equation, right? So we have k times d over d x of t, which is equal to k times d. So you can see that the k popped out. So that means it has the linearity property. When I scale the input, the output scales by the same value, even though the operation is now a differential. Right? So similarly, I can do the delay version. Let's take a picture, and then we will do the delay version. Give me a second to take notes. Yeah.
So the function is derived by x of t, right? Why did you put y not t in the beginning?
Because I just wanted to use a different variable that's not y, because I'm trying to find the effect of scaling.
Oh,
I have to call it something, so I just put a zero in there. Yeah. You can call it anything you want. That's not y.
I see.
Right. All right, so let's see what happens when you delay. So let's say there's a delay tau, and tau is a constant. So let's say y0 t is equal to d over dt x t minus tau. So we know that if t prime is equal to t minus tau, then t is equal to t prime plus tau. If I find the differentials, d tau is equal to dt tau plus d. This is a constant. That means this part is 0. So, sorry, this is dt. So dt is equal to dt. I can plug that in here. What I get is t x t prime over dt prime, and this is just a dummy. T prime is equal to. So the form of the operation remained the same. It's just differentiating. The only thing that happened was t became t prime, which is just a shifted version. So we showed that for the differential operation, the scaling, that's the same effect. It just scales the output by k. Delaying by tau has the same effect. It just shifts the time axis by tau, which is what we want. So differentiation is a linear and time invariant operation, right? So we looked at three now, right? We looked at scaling and delay first, and then we used those two things to show that, okay, differentiation is also falls under linear and time invariant operations. You can do the same kind of, simple scaling and delay operations on this to show that the integral also satisfies this condition. So that you should do by yourself. Okay? Think of it as a little homework. Use basic calculus principles. First do scaling. Scaling is a little easier. Just put k in there. You can see it pops out, right? And then do replace t by same kind of, dummy variable substitution, and you'll pop out the same kind of relationship for integration. So prove that at home. So homework submitted, but just do by yourself. Prove that integration also satisfies. Linear and time invariance. So let's use the knowledge. We showed that scaling and delay, differentiation and integration all satisfy linear time invariant operations, right? So now we can show that if we start with a differential equation, we can find the corresponding LTI system, or we can start with an LTI system with differentiators and integrators and show this thing is modeled in the mathematical domain as a differential equation. So let's look at a simple example. It becomes pretty obvious what you can do. So let's say you have a system which takes in x of t, right? It's a coefficient alpha, takes this coefficient beta, and you have d over dt operation. So we have two signal flow graph arms, branches. The first branch, sorry, the first branch is a pure scaling. Let me redraw it in a clearer way. Sorry. So let me redraw it. This and this is beta. So these are gains. And this is a differentiator. So the signal goes in the way it comes with just scaling in the first branch. The second branch, you scale it and then you find the slope, right? And you add those two together. You find a linear combination of the slope and the signal itself. And that is the output. So I can write the mathematical model of this. So let's say this is branch one. This is branch one. And this is branch two. So y of t is equal to something from branch one plus something else from branch two. Two contributions from the two branch, top branch and the bottom branch. So we can write down by inspection y of t is equal to the contribution from the first branch is simply alpha x of t plus, so this is the first one, and then the second one, 2, is equal to simply beta times d over dt. So I have alpha x of t plus beta d over dt x of t is equal to, you can also write this alpha x of t plus beta
X prime.
x prime or x dot of t is equal to So had I given you this guy, you should be able to draw this, right? This to that to this. Signal flow graph to math, math to signal flow. So as part of the course, you need to be able to go both ways. If I give you this diagram, you should be able to come up with this one. Or if I give an equation, you should be able to come up with the diagram. So let's do another example. Alpha 1, right? Alpha 2, d over dt, right? And then alpha 3, dt, dt squared, add them all up. Okay, and then I'm going to do a little trick. I'm going to take a copy of this. Let's say it is minus beta one d over dt. So I'm doing something weird here. I'm summing up the inputs, right? Input side has the direct path alpha 1, first differential path alpha 2, second order differential path alpha 3, right? So 3 branches. And on the output side, from here, so this is an intermediate step u of t. I take u of t and I have a feedback. So I'm feeding back the signal y of t back into itself with a differential coefficient in the middle, right? So this is called a feedback path. So this path, this is called a feedback. So feedback can be very well behaved or it can be nasty, it can be unstable. We are not going to worry about those aspects in this slide. Just look at the concept where you are sneaking back a copy with a differential coefficient back into the input so that the final output y is dependent on itself somehow, right? It's dependent on itself. So we have this system where you have input terms going in. So this is called the feed forward paths, right? So these are feed forward. And then you have the feedback. So you can have multiple differential coefficient orders in feedback also, but right now I just chose a simple version. So I can write down the relationship between y and x, right? So what's the relationship? Let me write it over here. I have y of t is equal to alpha 1 x of t plus alpha 2 dx t over dt plus alpha 3 d2x t over dt squared minus this part, which is what? Beta 1 d by d. I'm going to pull all the y terms into the left-hand side. So I have a mix of x and y terms on the left and right both. I'm going to collect all the x terms on this side and all the y terms on the right-hand side, right? Just to separate out the x and y. So when I do that, I'm going to write the x terms first. I get alpha 1 x of t plus alpha 2 x dot of t plus alpha 3 x double dot of t is equal to y of t plus beta times y dot beta 1. So this is a differential equation. Is it correct? Am I correct? Am I making any mistakes? No. So let's do a problem. Xt plus half t over dt xt plus 1/3 d2xt over dt square is equal to y of t plus 1/10 d2y. So I have three terms on the X side, the feed forward side. I have two terms on the feedback side. So I intentionally omitted the first dy over dt. I only have the second term. It's fine, right? So you can have any amount of terms and you can pick the order of the integral or differential operators that are happening. So in this case, I arbitrarily gave you something that doesn't have dy over dt, but it only has d2y over dt square. So what I need you to do is draw the diagram. So I'm going to pause the recording. Okay, we are back. We are recording. All right. Thank you, Nilan, for doing the problem. So 1 second just to get that on.
Wouldn't it be d squared over d2 squared for the bottom amplifier?
Yeah, it's really slow.
And the one of the left as well.
Yeah.
So what are those plus symbols signifying these graphs?
Addition.
Addition.
It just sums it all up linearly. All right, so let's do a problem. In class problem. And LTI system is given. Find or say plot y of t for x of t is equal to x rec t standard notation. So A is height. So like a small one. Let's do the integral first. It's a bit easy. Let me change it a little bit. Simplify. Let's say. So my input is the standard pulse, right? T is my x of t. My input side is just a pulse, like so. The height is a. This is minus tau by 2 to plus tau by 2. Duration is tau. Rectangular pulse. So the first step is to find out what the two different branches are going to do, right? The first branch is simply delaying and scaling, similar to what we did last week. The second branch is integrating and scaling, right? So figure out what the integral of the pulse looks like. Plot the first the integral, and then you just scale it by 2 down. So let's do it. So first branch is easy. So I'm going to draw in 2 different colors. So let's say first branch I will draw in blue. We'll draw in blue. And this part I will draw in red. And the scale version I will draw in green on the same plot, right? So let's do it together. So let's come up with the 3 components that we have to consider. I'm going to draw it over here. The y of t components. So this is not the y of t itself. These are the 2 components or the couple of components that we have to first figure out to find out what y of t is. The first one in blue is simply the input pulse shifted by t. So that's easy. So let's say this is t. So everything is shifted by t. We'll get a pulse that's scaled by 2 and shifted by t. So this is equal to t. This height is 2a now because it's scaled by 2. The red pulse is not delayed, but it's simply the integral. So you will get 0, 0, 0, 0, 0, 0 up to this point. There's no area under the curve. Then as you go along this rectangular pulse, right, it's a constant. So the first the integral of a constant is just a ramp, right? So you are going to see the integral grow as you go along. Let's say this, and then you have thing like that. Your integral is going to grow linearly with time, right? So it will grow. So at we have it like this. So this is at minus tau by 2, and then it will reach a maximum value, and then it will be. So what is the maximum value? It starts with 0. By the time it's gone all the way to plus tau by 2, this whole square region is now covered, right? So the area of a rectangle is one side multiplied by the other side. So this side is tau, the height is a, so it's a tau. So this point is a tau in height, correct? So my green curve will be simply twice of that. So I will get so this is 2 again. And it remains at 2 tau.
Is 2a tau or
2a, yes, sorry. 2a.
Where does the tau come?
Well, it's tau this way and a that way. So it's a rectangle. That's one side, the bottom side is tau and the height is a. So area under the curve, the integral is maximizing at a tau.
Okay, and the constant part?
Well, because once you jump off this edge, that integral value doesn't change, right? So it sticks at that value.
No, what I'm asking is the a tau.
Yeah.
Is that the function for the linear line or the constant?
It's the output of the integration, right? So you keep integrating, so you get nothing up to here, and then it grows linearly because the size of the rectangle grows linearly. At this point, it's the maximum.
Yeah.
Right, and then once it grows here, it doesn't stop. It stops growing. There's nothing there, right? So the integral part doesn't add up anymore. So it reaches a maximum of a tau and remains there.
A tau.
What is this area? This area, right? So this is tau and this is A. So it grows and remains, so this is A. So I can put this green curve and the blue curve together. So adding green and blue, it starts at minus tau by 2. Stabilizers at plus tau by 2. So the value starts at 0. This is 2A tau, right? Remains. And then it jumps by this much. So this height is 2A tau plus 2A, which is equal to 2A 1 plus E. And this is T. Looks right.
So is the A tau bigger than 2A or? Because I'm written, it's 2A is bigger than A tau.
Well, it depends on what tau is, right?
Yeah.
Like, but in this case, I consider tau to be bigger than 1, more than 1. So
So it would be bigger than 2A.
but A is a height and tau is a time. So yeah. Yes.
Okay, so okay, so let's see if so I noticed the way that you need to look at okay, so assuming for okay, so okay,
So I found the individual contributions from the top one and the bottom one, bottom part. The bottom one, I found it in 2 parts. I mean, I could have directly found the green curve, but I first found this part and then I scaled it by another 2, just to make it easy to understand, right? So this part is purely integrating. So it goes with 0, rises up as you go through the square region, it linearly goes up. And by the time it hits this edge, it has reached its maximum value and then it remains at that maximum value because there's nothing else under the function from that point onwards,
okay.
right? So, but that whole thing is scaled by 2 at the end of this signal flow.
Okay.
So that's why it jumps to twice. This is A tau, this is 2A tau, this is the result of this scaling. So this green curve is linearly added to the blue curve. So this remains at this point, this jumps up and comes down. So that's why we have this tick, jump up.
Oh yeah, and as for the top one, you basically it's just shifting the graph, right?
Yeah, and scaling by 2.
Okay.
So you got to get your mind around it. You can do manipulative things on the signal. You can scale it. You can delay it. You can integrate it. You can differentiate it multiple times over and sum them up.
So the integration, what it does is basically it turns the thing into a linear.
Well, it turns it into a linear line because the pulse is rectangular, right?
Pulse.
So when you integrate a rectangle, it linearly increases, right? But depending on what the input is, the integral function looks different, right? So let's say it was not a how do I put it? So let's take another example where my function is x of t is equal to t. Okay, so if my function is x of t is equal to t, the integral of this, right, is what? It's equal to something like e squared by half, right?
Yeah.
right? So this is a quadratic. So when your x of t is like this is my t, right? Then my t squared is something like that. It's a parabola. So it became linearly increasing simply because my input function was rectangular. That's the integral of the rectangular.
Because your integral was, integral of one dt, so that was now. It turns it just into a constant.
So it turns into a scale value of t. So when you find the integral from the limit, it's just you're integrating just a rectangular box, right? So that is just a dt integral, right? So you have something like, okay, integral minus tau by 2 to plus tau by 2 a d lambda, right? So this will go a minus tau by tau plus tau by tau d lambda, which is equal to a.
Wait, why is it now not lambda?
So lambda is just a dummy variable. You have to have some variable to integrate.
So I don't.
Integration of a constant.
But I thought
Perfect.
integral of one, dx is just x.
Yeah, exactly. But instead of x, we have
Oh, so, okay.
So in this case is for the first graph on top is the green function. The result of the first branch and the blue function is the result of the second branch.
the green function is the result of this branch, the bottom one,
The bottom branch.
right?
Yes.
And the blue function is the result of the top branch, which is purely delaying and scaling. There are no integral operations. So I didn't introduce any calculus operations in the first one, but the second one I'm putting in a simple calculus operation also, just to make the point that you can have it on there. So every time you make a circuit which has only resistors and transmission lines, you have things of this sort, scaling and delays. But the moment you have inductors and capacitors cause the signal to be integrated and differentiated. So we need to know how to manipulate circuits which have inductors, resistors, capacitors, and delays. Yes.
For the first graph.
Yeah.
I think the x line is t, but the second graph it's tau, it's tau.
No, it's T. That's just me, my terrible handwriting. It's T. This is tau.
Could this be a mental model of, how I see like the linear line? I can just see the integration of 1/t is equal to tau, right? And then you would have to add the a in because the a is the constant. And then I see it as the a is a scale number, it could be anything, and tau as the variable.
Yeah.
And that's the linear line. Could I see it like
Right.
that?
But tau is not a variable. Tau is fixed. It's the size of the pulse. I mean, you can change it. It's a parameter. But as far as the calculus part is concerned, it's considered as a constant. It's not part of the differentials of the calculus operations, right?
So don't think it as a variable.
It's a parameter, right? So you fix that, and once you fix it, you can make it whatever you want. But once you fix it, it's constant as far as the calculus of this variable is concerned. Right? Once you find the answer, you can select or to be any value that you want. So it's a constant, right? But you can change it, but once you change it, it's not going to change as a function of something else.
Why are why is it minus tau over 2 to tau over 2 again?
Because we said it so.
Okay,
We defined it that way.
so in the problem, it'll be defined.
Right.
that way.
So when we say a standard rectangular pulse, its duration is tau. It starts from negative tau by 2 to plus tau by 2, right? By symmetry. That's just chosen arbitrarily to make the math simpler.
So question, I saw that in the last class, I was kind of confused on why new graph, like the second one, goes up to the delay function, because for example, like you said that the 2A2 was a result of the branch, of the second branch.
Mhm.
So why does the result from the first branch go up Why is it affected by it?
Yeah, well, because we are adding them up, right? So when we add this green graph to the blue one, even though this starts from 0, when you add this to that, it has to go from here on up. Right? It's stacking on top of each other when you add them up. Individually, they are in these ranges, but when you add them up, so let's say this goes from 0 to 1, and this is let's say 3. So then this is 3, and then this goes from 0 to 1. So 1 plus 3 is 4. It has to jump to 4 now, as the result of the addition. All right, so we have to move on. So on Thursday, I'll be in DC doing some FIU business travel. So we will have a demonstration for you guys right here. So make sure you come on time, and our TA team will show you some cool stuff. Okay. So I'm going to leave you with a definition of the frequency domain. We'll talk about this in detail next week. So if you have a signal as a function of time, call this x of t. This by x of t. So this signal has to have some mathematical properties, which we will go through in future classes. But for now, think of this as a Fourier transformable signal, right? We are going to find something called a Fourier transform, and find a Fourier transform. So we can call it a finite energy signal. So there's some mathematical operation that is linear and time invariant, defined like so. So we have a variable x of f is called frequency. Right? So this is capital X, and this is complex value. Okay. So the result of the function that we are defining, even if my input signal is real valued, can be complex value. Okay. So in general, it's a complex function, and this complex function is defined as x of f by definition, the integral from minus infinity to plus infinity, x of t, which is the signal, right, times e to the minus j 2 pi f t So I can think of this part as some v of t. So this v of t is complex value by itself, right? Because this is complex value. This is the complex exponential function. So think of this operation. It's a complicated math formula, but you can interpret this as a bunch of things. So you have x of t coming in, and you multiply that with another function called e to the minus j 2 pi f of t, where this is my frequency value. And it produces an output v of t, which we stick into an integral box. Which gives us a complex valued function. So we are using the properties of linear time invariant systems. We proved that the integral operator is linear and time invariant, but we are replacing the pure input x of t with a modified version which has this extra part. That's a modulator, right? It's multiplying the signal x of t with a complex valued function that has a particular behavior. We'll go through all that. But think of the concept. You have the signal coming in, but instead of directly integrating it, we do some funny business here with this multiplier, right? And the resultant of that is the thing that we are integrating. So that by definition is called a Fourier transform. Okay. The signal of interest has to meet certain mathematical properties, which we will go through in future classes. But at this point, I want you to be familiar with this formula. Believe me, it's not as nasty as it looks once you get used to it. It's a pretty simple formula, but looking at it for the first time, it looks a little daunting, okay? But really, once you get used to it, it's a very simple thing. So I want in your mind's eye to imagine the signal getting modulated by a multiplication operation, right? And the resulting signal, V of t, is getting integrated. So we can do this multiplication and integration operation for various values of f, right? We do it for one value of f, another value of f, another value of f, and every time you change the value, the resulting function value is different, right? So we can keep changing f, and we can plot the value that's coming out as a function of f. So this is f, and this is my x of f. So if I keep doing the operation multiple times with different values of f, for every value of f, I'm going to get something out. So this is my x of f. So this going from a function of time to a function of f gives you a complex valued function which has a real and imaginary part, and that mathematical operation is defined as the Fourier transform. So with that, we'll end today and we'll take it up in the next class.